So this is our introduction to what I call node-based computational programming. Um, and the tool that we're going to learn first is Dynamo, and I'll explain more about some of the other software that's available. And obviously this first image is kind of a joke about this idea that whenever a new college professor who has computational design background or the start of an academic year and a new leadership is involved. One of the exciting ways of expressing how smart or sophisticated the school is to create some kind of a structure is this based on the ideas of computational design. And if you Google the term computational design, you'll get a lot of these kind of really far out types of structures. And while that's an important part of what we're going to talk about, it's not really the whole story. And it's not, if you're not engaged in this idea of this kind of structural manifestation or creation, I hope you'll still tune in and be interested in this to kind of see the other aspects of where the value of computational design thinking is going. Um, so, in the um, there's really no easy way to give you one standard definition that you could hold on to this concept. The way to really build this out is to explain a lot of the things that are done with this technique and do some relationships to it. And by the end of the first part of this lecture, you should have a good handle on what we're talking about. So when I talk about node-based, I'm really referring to this kind of graphic that we see up on the screen, that our coding environment, our manipulation of our design intent, which is actually resolved down to numbers at this point, numbers and objects, um, are really based on these little icons that funnel data together or apart or go and grab components. And they're actually literally wired together with strings that you pull out from each one of them. And that indicates a path that data moves through in order to accomplish different kinds of tasks. And I show you that we're going to learn Dynamo, which is up on the top. And actually, the interface has changed a little bit since I produced this graphic. And down below is another piece of software that's often discussed, and that's Grasshopper. And that's part of the Rhino 3D modeling environment. But one of the outcomes of learning this idea of how to design using numbers in computational design is that once you learn that, it will be useful for you in a whole host of other types of functions that you might want to accomplish. This is just a side issue about this idea of when we talk about computational design, many times we come kind of closely aligned with this idea of parametric design because parametric design is about designing to parameters, numbers, and this is obviously what's happening. And this is an interesting article that I would link you to. I'll click out to it quickly. And this is a promise and peril, so it gives two perspectives of what it ends up being Zaha Hadid's exhibit on parametric design. And I think one of the interesting things about it, if you scroll down and read through this, is that the statement that Zaha Hadid thought math was like sketching. So this idea of being able to play with numbers and realize design. So this is an interesting exploration of an architect who really took the idea of math and computational design and really embedded it in her architectural work. So back to our presentation here. So we're going to, in the course of the course, go through some computational design techniques 3 or 4 times. And that should give you a pretty good introduction to overall how you can use and take advantage and or just understand what other people are doing when it comes to ideas of computational design. But I wanted to point you to some resources for learning. If you're really into ramping yourself up the learning curve quickly, Mode Lab has created a primer that really goes through and describes all of the levels of functionality with inside of the dyno, or just basically any computational modeling environment. And so this is hyperlinked and you can go to it and this will take you to that primer. If you actually start the Dynamo software, they have a link, I think it's still embedded in the site, that will take you to that primer. The other The other way to gather information or more sophistication beyond what we're going to learn in the course is to obviously subscribe to YouTube people who are leaders in the field. Jeremy Rowe here, really strong in his development of ideas and methodologies for teaching computational design. And then Zach Cron, who still has a presence on the internet. I think that these will still be live. Very interesting ideas about just all kinds of ideas about computational design and parametric design and the powers of it. And he's now an Autodesk employee, so I'm not sure how much he maintains his other sites on that. And then once you learn some of the nomenclature, like for instance, lunchbox, and really there's just a whole host of really odd terms that are used with the software. Once you start learning some of the names of the tools that are available within the environment, there are many sites that go into depth with explaining how to take advantage of the powerful tools that they have. And in the next bunch of slides, I'm going to show you some general applications for this kind of computational programming. And then hopefully you'll find the area that you're most interested in, and that you could probably find the most engagement in it. But overall, I would hope at the end of this course and at the end of leaving this project that you could recognize computational design when you see it manifest in something, and then be able to look at the source code, the node-based programming, and realize kind of a general flow of what might be going on within it. So I showed you these really complex shapes that are being generated with computational design, but there are so many other kinds of ways to take advantage of this idea of grabbing the data with inside of your model and manipulating it for all kinds of reasons. And that could be really kind of very mundane, but very powerful features. Like for instance, if you wanted to add a dimension to a room tag, or you wanted to make a statement of the amount of square footage and that functionality wasn't already implied in a tool in the tagging, you could actually write a script that would do that calculation for you. So you can do things that would really increase your productivity as a draftsperson, as a production person who's in charge of making the technical drawings for your firm. The other advantage is the ability to do really more complex analysis. For instance, this is a way to do a much more advanced sun study over not only one day, but over the course of a year to find out where the maximum amount of sunlight falls on a site. And it's really built up on some very simple ideas of computational programming. Back to another computational tool. And I'm showing this for two reasons. One is if you look on the left, you'll see the code looks very complicated. And I don't know if I have the, yes, I do. I'm going to back up one more and before I go to that. But here's an application where you may have been requested to take room functionality and create a model that shows that color coded in the 3D visualization of it. And you could go step by step through each room, pick out the room, add the color volume to it, and then go on to the next room. Or you could write code, which at first looks really kind of overpowering to you. But if you understand the code, you can look at each little snippet, as I put in this red box, and realize that each one of those, going all the way down that whole list, is just the same element copied over and over and over again. And so the idea is grab the room tag, find out what it's been assigned to, then in the code, assign it a color and a volume, and run the program, and all of a sudden all of these are populated. Now, you might say, well, that's going to take me as much work as identifying each one of those rooms. And that could be one way of looking at it. But now imagine that you're now faced with another building to do the same task, or another 10 buildings, and or somebody decides to change the layout of this facility and move some of those around. And now you're taxed with the idea of identifying which one is changed and how to change the color to it, and do that manually. So in this case, this automation can really simplify workflow in ways that can just cut hours off of your times and activities. So there's the idea of that kind of code replicated on through. And then there are things that kind of show you the breadth of what is available. This is a grasshopper node-based definition, but here we have a wireframe with a uniformly distributed load over it, and now a way of doing structural analysis within inside of the programming environment to determine sizes and deformation of elements. And in our projects, this is one that you won't have this year, but in past years, I've done the idea of creating a complex truss system, a truss that's following the pattern or shape of the facade itself that might be undulating, and then building through computational programming all of the truss elements that are needed to create that structure, and doing that automatically. So for instance, you program the first truss, then you tell it that you space them out on a certain module, and each one will conform to the shape of the facade. Just a very powerful way to use computational design. And this is one I include because I worked so hard on it, but I've thrown it out. The ability to actually create a truss and look at the amount of stress and strain that is occurring within inside of each one of those structural elements. So this could be a truss that's inside of your Revit BIM modeling environment, and then we bring it into Dynamo and do this kind of structural analysis on it. Some things you may not have thought of yet that may you may become aware of in practice, especially if you're working with complex shapes. The ability to determine which things are planar and which things are not. So for instance, this curvilinear surface has been mapped with flat panels. And the idea is at what point does the flat panel exceed a certain amount of misalignment with the next panel because it's flat? We're curving flat panels over a curved surface. So at some point at that seam, there is some kind of a misalignment. And then the idea is to determine where those panels might have the most amount of misalignment, and then determining how we might manipulate the way we do the panel layout. Another thing that we can do with computational design that's extremely powerful is to create a shape and then be able to unroll that shape onto a flat surface so that we could cut the panels, the wood, or whatever element is in order to make that shape. And you could see here the code can get quite complex for those kind of techniques. So I'll end this and we'll pick up on computational design examples, and we'll start with ceiling systems next.